Hello, everyone, and welcome to my presentation about codes for cost-efficient DNA synthesis. So this is joint work with Yi Liu, Cyrus Vashtian, Paul Siegel, and Andrew Chan from UC San Diego, and together with my PhD supervisor, Antonia Wachtertze, and together with Eitan Jacobi from Technion. All right, so let's dive into the topic. So the outline is as follows. So first of all, we will go over the general system model and the problem for formulation of efficient DNA synthesis. Then we will go and talk about synthesis, subsequences, and graphs, and see some connections between these three, and also relations to cost-constrained systems. Finally, we are also going to talk about the case where the DNA sequences have fixed length sequences, and we will give a short conclusion in the end. All right, so how does data storage in DNA usually look like? So first of all, because it's data storage, we have some binary data that is going to be stored inside DNA. And the first step to store it is to encode it using an appropriate mechanism into DNA strands, which are basically vectors over the alphabet of A, C, G, and T. Then these strands, which have been encoded, are going to be synthesized, which means they are artificially created by a synthesis machine to be actual physical DNA strands, and then put into a storage container where they are stored until one wants to access the data with a DNA sequencer, which basically just reads the strands as they have been stored, but possibly with errors. All right. Now, how does this synthesis process look like, which is going to be the focus of this talk? So what we're going to focus on is array-based synthesis, where the synthesis is performed by a nucleotide by nucleotide parallel synthesis of DNA strands. And how it works is that you select a synthesis strand, and then you flush nucleotides over an array, and then you select certain points where you want to attach this certain nucleotide that you just flushed, or just leave it away. So, and let's go over a short example. Say, for example, I chose in advance the synthesis sequence ACGT, which has length 8. Then, and I want to synthesize 3 different sequences. First of all, CTACG, AGTA, and CTD. So all of them I want to synthesize in parallel, okay? So what I do first now is in the first cycle, I flush A over my array and I attach it to the strands where I want to have an A. And in this case, this is only the second strand because the 2 other strands begin with a C. Now, next, I flush the array with the C and attach it to those strands where I want to have a C, which is strand 1 and 3. Now I continue this process with G. I attach G to the second strand. Now I attach T to all of the 3 strands. Next, I attach A to the first 2 strands. Then I attach a C only to the first strand. Then a G only to the first strand. And finally, a T only to the last strand. So as you see, we have in the end, we have synthesized all 3 strands that we were looking for. However, notice that not in every cycle, it's possible to attach a nucleotide to every sequence, just because these strands or the sequences to be synthesized might be different. So we cannot guarantee that we synthesize in each cycle on each strand. Okay, now let's go a little bit more formal and talk about the problem setting. So say we have a parallel synthesis of K strands, where K was 3 in the previous slide. And they are just arbitrary length sequences over an alphabet of size Q, where Q is equal to 4 for ACG and T in DNA. Now we choose a common synthesis sequence S, which was the ACGT in the previous slide. And then with that, we can define the synthesis time of the strands X1 to XK using a synthesis sequence S. And this is simply defined as the smallest time t such that every strand Xi is a subsequence of the supersequence of the prefix of the supersequence of length t, which means basically, as you have seen before, that we are synthesizing in each step, And T is the number of steps that we need to do until we could synthesize all of the strands. Okay, so let's go back to our previous example. So this is exactly the example from the slide before. There we have seen that the synthesis time is 8 because we needed 8 synthesis cycles to synthesize all of the strands here. And notice again, so this 8 is larger than, or at least the length of all of these sequences, because we couldn't synthesize to every strand in every cycle. All right, now let's go to the problem formulation. What we are going to do is we want to restrict the sequences to be synthesized to a specific code, which is denoted by C, and this is just a subset of all of the sequences over the alphabet Q, such that the synthesis time is small, okay? And in other words, what we are trying to achieve is we want to maximize the information synthesized in a specific time, capital T, which means that we're looking for maximizing the size of the code such that the synthesis time of all of the strands which are in this code is less or equal than T. And then we will denote this maximum size of the code by n of S and T. And note that here we only restrict ourselves to one strand to be parallelized. And this is due to the fact that when we fix our supersequence S, actually, it doesn't matter how many strands in parallel we synthesize. All right, let's go. Okay, so here, just as a reminder, this is the maximization problem that we're trying to solve. So we want to maximize the size of the code such that the synthesis time is less or equal than T for all code words. All right, so based on this, we can define the maximum information rate per cost time, which is simply defined as log of n of S and T, which is the number of bits that we can synthesize, divided by the total cost, and then we let the cost go to infinity. All right, so by this definition, this rate, or also capacity, what we call it later, is measured in bits per synthesis cycle, because this is how many bits we can synthesize per cycle of the previous synthesis process. All right, so now what is the contribution of our work here? So first of all, we characterize this R of S for arbitrary periodic sequences, or synthesis sequences, using cost-constrained systems. And also we highlight parallels to the subsequence spectrum, which I'm going to define later. All right, but to do this, we first need to talk about an important entity, which is the subsequence graph. So how do we build this graph? It's simply built by choosing as vertices the symbols of the synthesis sequence S, and we have edges which are defined as follows. So for each vertex, we have Q outgoing edges, where Q is again the alphabet size, 1 to each next appearance of all the symbols in our alphabet. Okay, so this is maybe a little bit abstract, so let's go through an example. Here we have our favorite synthesis sequence, ACGT, ACGT. And now, so these are the vertices of our graph. And now we build the edges as described here. So we start with A and draw an edge to every next appearance of all the symbols, which means we draw an edge to the next A, to the next C, to the next G, and to the next T. Then we do the same thing for the next symbol. All right. Also, we have 4 outgoing edges here. Then we do the next thing for G. We do the next thing for T, for A, C, G. And this is our subsequence graph. Okay. And all right. So now you might ask, why do we build this graph? And the reason for this is that the following observation, that X, so a sequence X can be synthesized if using this supersequence S here, if and only if is obtained by some path through G of S. And this is very natural and almost trivial observation, because this just follows from how the synthesis process works, right? All right, and this brings us to the following lemma, that the largest size of the code, of our synthesis code, is just equal to the number of paths through g of s1 to t. So the prefix of, so we take the graph of the synthesis sequence of the prefix of length t of the synthesis sequence. And all right, so maybe a short notice here, it says informal here because of the fact that actually we don't count all the path through g of s and t, but we count only the path from which start at one of the first four vertices, in this case here, because otherwise we might actually have different paths which generate the same word, and therefore we would have an overcounting on the right hand side here. So if you think about it, if you would start here, A and C, you could generate it also with going from A and to C here, but this is what we disallow. We actually only allow to start from vertices from the first four vertices here. All right. All right. Then now, what is the subsequence spectrum? It's just all words that are obtained by deleting symbols from a sequence S. Okay. So as an example, we start with the sequence ACG here. So the whole spectrum now is all the words which can be obtained by this word by deleting arbitrary symbols from the sequence. All right, now the next observation is that actually the largest size of the largest synthesis code is equal to the size of the subsequence spectrum of the supersequence here. And again, this proof is rather straightforward, and you can prove it by simply left aligning all these subsequence here in the subsequence graph, which we have seen before. And then we see actually that there is a one-to-one correspondence between a subsequence and a sequence that is synthesized. All right, then this brings us to the following three equivalences here, which we have already mentioned, that the largest synthesis code is equal to the number of paths through this synthesis graph, and this is equal to the number of subsequences of the synthesis sequence S. All right, just as a side note, actually, as it is known, with these equivalences, actually, we can show that the synthesis sequence, which maximizes the size of the code, is the alternating sequences. And this is because the alternating sequence maximizes the subsequence spectrum, in fact. And therefore, it also maximizes the synthesis code size. All right, so let's talk about a little bit more about periodic sequences and our asymptotic results. So what is a periodic sequence? It's just a sequence which you can write as the concatenation of some smaller sequence S, where S is the period of the supersequence of the whole sequence S, and L is the length of the period. All right, so for example, if you look at the synthesis sequence, which is AAC, which looks like this and has the corresponding synthesis graph like this, then the period would be AAC in this case. All right, and in this case, actually, we can reduce this large graph to a smaller, easier graph, and with only L vertices, which correspond to every symbol in one period. And it is created as the same, so we take the symbols of one period and we draw the edges in the original graph, but we have to add another stage, which is actually a weight of the edges, which is simply the size of the step that you would take in the original synthesis graph. So in this case, we have here 3 vertices because we have period length 3. And then, for example, if you go from A to A here, which corresponds to this step here, it's a step size of length 1. So this this edge has weight 1. Similarly, if you go, for example, from C and then again to C, you see that you skip 2 A's and therefore you have a weight of 3 here. All right. Now with this periodic synthesis graph, actually, what we can do is we can formulate the same lemma actually that we have for the non-periodic graph, which means that the size of the largest code is equal to the number of paths through G of S, but now with the difference that the sum weight of a path must be at most T. All right, and with this, if we define edge weights tau of I and j to be the cost from vertex I to vertex j, then we can say actually that this periodic subsequence graph defines as a cost constraint system. And this is very powerful because we can use all the machinery that we know about cost constraint systems for our synthesis problem. All right, then one theorem directly follows. So if we define C of S to be the combinatorial capacity of a constraint systems, which is just defined as in the standard as in the standard constraint system theory, as the size of the language of sequences with size of at most T, and then you let T, the size of the language of sequences which cost at most T, and then you let T go to infinity. All right, then we get this theorem here that our maximum synthesis rate, which was defined as log n of S and T divided by T, that this is exactly the capacity of the combinatorial system because their definitions adjoin, in fact. Okay. All right. Then what we can do is we can use results from constraint theory to find this R of S. Actually, by finding this capacity of the cost constraint systems. So say we have a graph G of S with edge weights T tau ij, then we can define this L by A adjacency matrix, which is defined as 0 if there is no edge from vertex I to j, and 2 to the minus z times the weight of going from vertex I to j. And yeah, then if we find the largest solution to the determinant equation, that determinant of 1 minus this matrix P of Z is equal to 0, then we know that the capacity of the constraint system is equal to Z0. So this is a well-known result from constraint coding theory, and we can use it also in our case. So for example, now if we look at our favorite example, the alternating sequence, ACGT, ACGT, then we get this as our P of Z matrix, and we can find actually that the synthesis rate, which we can synthesize here, is Z0, which is 0.947 bit per cycle. And now, interestingly, actually, if we compare this to the uncoded case, we only get a synthesis rate of 0.5 bit per cycle. And this is because if you don't code the sequences, it might happen that you synthesize a sequence such as AAAAA, which has a very large cost because you have a cost 4 in every step, and therefore you only can synthesize 0.5 bit per cycle. All right, for arbitrary Q, actually, what you get is that you have to solve this determinant equation and find the largest root of this one, and you will get the capacity of the system. All right, so furthermore, we have looked at explicit codes, not only at capacity, but also at codes which actually can achieve rates that are close to this capacity and also are efficiently encodable and decodable. So because we are living in a cost-constrained system here, one possible way how to build codes is WAN codes, which are explicit prefix codes for cost-constrained systems. And they are constructed via tree expansion as follows. And what we see here is a plot of a codebook size, of the achievable information rate that we can achieve with a certain WAN codebook size here, and where the codebook size is chosen to be certain powers of 4, in fact, to match the DNA alphabet. And what we see here is that already with quite moderate codebook sizes, we can achieve information rates which are fairly close to the capacity. If you remember, the capacity was 0.947 bits per cycle. And here, for example, if we take a codebook size of 4 to the 8, what we get is an information rate of 0.928 bits per cycle, which is fairly close to the capacity. All right, then let's shortly talk about fixed length sequences, because for now we have actually said that the sequences that we synthesize can have arbitrary length, right? But now if we restrict our sequences to have a fixed length n, which might be due to practical reasons or also due to synthesis constraint, then we can do the same definitions as we had before. We can define the largest synthesis code, where now we have a super sequence S, a maximum synthesis time T, and a fixed length N. All right, then what we get is the information rate per cycle we defined similarly, where now we fix the length not to be arbitrary, but to be some fixed constant of the cost, which is alpha, where alpha is just a constant which is between 0 and 1. All right, then we have the same equivalences actually as in the variable length case, because here again the largest synthesis code, it relates through a length n path through this synthesis graph and also to length n subsequences. So this is also directly true. And going through a small example. So for example, if we look at the binary alternating sequence AC, then what we can show is that using combinatorial results from about subsequence coding problems, we can show that the R of S and alpha, so the maximum achievable information rates in bits per cycle for a specific length alpha is given by this function, which if we plot it like this, looks like this. And we see that its maximum is obtained by roughly 0.72, I believe. And note that actually this maximum abscissa here, so the maximum over alpha, corresponds to the rate that we can achieve without with variable length codes. All right. Then to conclude this talk, what we have done is we have talked about time-efficient synthesis. We have shown correspondence between optimal synthesis code, path through a graph, and subsequence. And we have shown a solution for arbitrary periodic sequences using cost-constrained coding techniques. Again, this also implies results for asymptotic growth rate of number of subsequences, which is interesting in many combinatorial questions. So what could be outlooks for the future? One is incorporate error correction, because when we do DNA-based data storage, as we have seen in the beginning, there are errors inside the system which we want to combat. And so we need to incorporate some error correction. Then also we could incorporate the fact, so for now we have looked at the setup where the synthesis sequence is fixed, but we might also want to actually change it according to the sequences that we are actually synthesizing. And this brings me to the end of my talk, and thank you for your attention. I'm looking forward to your questions.